Hi, my name is Martin. I'm the head of research at mneomonic. I'm here to talk about adversary emulation, more specifically on how to generate sequences of techniques from MITRE ATT&CK. First, a little bit of background on adversary emulation. We defend against real adversaries. And in order to test our defenses, we should test them against real-world adversary behaviors. And we can do that by using adversary emulation. In order to do that, we need a plan, an adversary emulation plan. This is an example of the first adversary emulation plan published by MITRE on APT3. And the figure shows the different phases of the attack and the activities that the adversary performs within each phase. Now, adversary emulation plans have developed further since this plan was published, and the current state of the art is that an adversary emulation plan consists of three main components. The first is the intelligence summary, which gives a general overview of the adversary with references. The second component is the operational flow, where the techniques used by the adversary are chained together into a logical flow to show the progress of an attack. And the final component is the emulation plan itself, step-by-step instructions showing each command executed by the adversary at that step. Making adversary emulation plans require a substantial amount of time, expertise, and effort, and is largely a manual task. So one of our goals was to see whether or not we could automate parts of this process to speed up the creation of adversary emulation plans. Now, adversary emulation plans are based on MITRE's Adversarial Tactics, Techniques, and Common Knowledge, also known as ATT&CK. An ATT&CK is a curated knowledge base and model for adversary behavior. MITRE ATT&CK consists of the following core components: tactics that are tactical adversary goals during an intrusion. Examples include initial access, persistence, lateral movement, collection, exfiltration. Then the second component is techniques, and techniques describe how an adversary achieves these tactical goals. So one tactic can have multiple techniques. Sub-techniques are in principle the same as techniques, they just have a more detailed description. And finally, MITRE ATT&CK contains information about adversary usage of techniques, what kind of software they use, descriptions of their procedures, and other kinds of metadata. MITRE ATT&CK has an object relationship model, which is shown here. So in the top left, you have an adversary group. This adversary group uses techniques and sub-techniques, and they also use software. And that software implements techniques and sub-techniques. ATT&CK contains mitigations that prevent techniques, and finally, techniques and sub-techniques accomplish tactics. As you might notice, there are no relations between techniques and sub-techniques here. So MITRE ATT&CK does not contain any kind of information on what relations or dependencies you have between techniques. And that's an issue if you want to chain techniques together. So our problem statement, what we tried to solve, was to generate the operational flow of an adversary group or a campaign or an incident. That means you can spend the time, expertise, and effort once, and then reuse that every time you want to generate a new operational flow. There is some previous work on this topic. MITRE Caldera is a tool for automated red teaming. And Caldera has a concept of preconditions and post-conditions for attack steps that are mapped to techniques. Andy Applebaum from MITRE took this a step further at the first conference in 2019, where he presented how to use Caldera to chain techniques together in MITRE attack. Now, the limitations of this previous work is that it doesn't cover all of MITRE attack. It only covers the techniques and sub-techniques that are defined in MITRE Caldera. And second, it's tool-centric to MITRE Caldera, because the preconditions and post-conditions in Caldera are very closely tied to the toolbox that Caldera provides. So we wanted a general way to describe dependencies between techniques in order to generate chains of techniques from a threat actor, incident, or campaign. And to achieve that, we applied promise theory. I will not go into the details on promise theory here. If you're interested, there's a link at the bottom to the paper that introduced it. But I'll give a very, very simplified explanation of how we use it. So promise theory consists of autonomous agents and promises. And a promise is a statement of intent. Basically, an autonomous agent saying, I can provide this. And as opposed to the classical way of thinking, where one agent would call another agent and ask it for something. So give me this, like a function call or a web request. In promise theory, each autonomous agent says, I can provide this. And then the agent that needs that promise will look for other agents that provide it, that can give it to it. And then this agent might again provide promises that are required by other agents. So the advantage or benefits of using promise theory is that it's scalable. There's no explicit coordination between these autonomous agents, so they can self-organize. And it's distributed so that you can view each autonomous agent without considering all of the other autonomous agents. So the way we use it in a general model is that we view techniques and sub-techniques as autonomous agents. And then each technique or sub-technique has a set of preconditions or requires that are promises that are needed to execute the technique. Furthermore, it also has a set of post conditions or provides, which is a set of promises that are provided after executing the technique. And since every technique and sub-technique is autonomous, analysts can review them separately, and they don't need to consider anything else than the one specific technique they're assessing here and now. But one example just to illustrate this. This is a technique, remote services, from the lateral movement tactic. It has a requires section with 4 promises: access network, credentials users, info network hosts, and info network services. Access network means that it has access to the internal network of the target infrastructure. Credentials users means that it has access to valid credentials for multiple users in the infrastructure. Info network hosts means that it knows about hosts and addresses of other systems in the infrastructure. And finally, info network services means that it knows what kind of services that are running and listening on network ports in the infrastructure. Finally, there's a provide section, and it provides the promise moved laterally. Moved laterally means that the adversary is now no longer constrained to the single system where they gained initial access. They have moved and they have access to several different systems in the target infrastructure. Another, a little bit more elaborate example with 2 techniques. So here we have the phishing technique and the user execution technique. The first promise I'll show is info email address. This promise represents the knowledge of a valid email address in the target organization. and you see an incoming arrow to phishing. That means that phishing requires info email address in order to execute. Once executed, phishing provides tool delivery. Tool delivery means that you have the capability to upload or deliver an arbitrary payload to a target system. Tool delivery is required by user execution, but user execution also requires another promise called tool available. Tool available represents the fact that an adversary has access to a tool or malware. And that's different from having the capability of delivering a payload to a target system. So user execution requires both. And as you might see, in this picture, we have no techniques that provide info email address or tool available, which means that by themselves, these two techniques cannot be executed because they require promises that are not provided by any other techniques. Finally, user execution provides 4 promises: privileges user local, access file system, access memory, and code execute. So the approach we wanted to be able to generate these sequences or chains of techniques. And we started out by developing a vocabulary of promises. The first thing we did was to investigate sticks and mic vocabularies, but we couldn't find any that were at the right abstraction level to fit techniques and sub-techniques in MITRE ATT&CK. So we started developing our own vocabulary, and then we reviewed all techniques and sub-techniques in MITRE ATT&CK, and we defined which promises are required by and which promises are provided by every one of those techniques and sub-techniques. We also developed a tool that could generate attack stages based on this information. That tool is open source. It's on GitHub on the link on the bottom of this slide. I'll give a demo of that tool a little bit later. And this was an iterative process. So we did one pass at this, then we went back, expanded and refined the vocabulary, reviewed the techniques again, improved the tool, and cycled through like that for several iterations. So we're not done with this work, but we've gotten to a point where it starts to become useful. And we hope that this tool can be useful to other people as well. So to give a very brief overview of that tool, the tool takes 3 inputs. The first input is a list of techniques and sub-techniques. It supports attack navigator layers, but it also supports a very simple JSON format, which is just a JSON list of technique and sub-technique IDs from MITRE ATT&CK. The second input is the definitions of the requires and provides for each technique in MITRE ATT&CK. We have a big JSON file with all those definitions on GitHub as part of the data for this tool. And the final input is the end condition or objective. And that could be exfiltration, destruction, extortion, denial of service, representing what the adversary tries to achieve by this intrusion. Some techniques provide these end conditions, and in order to reach it, you need to execute one of those techniques. When executed, the tool initializes by creating an empty queue. And then for each attack stage, it executes all techniques and sub-techniques where all promises in the requires section of that technique are present in the queue. That also means that for the first stage, only techniques with no requirements can be executed. Next, it adds all of the promises in the provide section of the executed techniques to the queue, and then it advances to the next stage and does this all over again. And it keeps doing this until it is unable to execute any more new techniques or sub-techniques. The output The main output is a table with the stages of the attack and the corresponding techniques and sub-techniques, but it can also display the tactics that those techniques belong to and the promises that were provided during that stage. And finally, it outputs a verdict. And that verdict is whether or not the end condition that was given as input was achieved, given the techniques that were available. So I want to give a quick demonstration of what this tool looks like and how it works. The tool on GitHub is command line, but we have a prototype web interface, which is shown here. And in order to run the tool, you first have to select a threat actor or incident. So for this example, I'll use the Lazarus group. Then you need to select an end condition. So I will choose objective exfiltration, which means they want to find the information they're after and exfiltrate it. I want the tool to show the promises that were obtained or provided during its stage, and then run it. So when I do this, the first thing that happens is that the tool says it failed, incomplete attack chain. And the only thing that happened was that at stage 1, it executed brute force password spray, which provided credentials user local. And then nothing more happened. And the reason for that is that the techniques associated with Lazarus group in MITRE attack are not sufficient to be able to carry out an intrusion. So in order to see what would happen if they had other techniques, I can give them the technique gather victim identity information, which will provide them with a valid email address in the target organization. The technique ID is 1589, so I'll just add that and then run it again. So now this is the technique that I gave them, gather victim identity information. And what happened is that they are now able to launch a phishing attack, as you saw in the previous example with phishing and user execution. You might remember from that example that user execution also required two available. And that's actually what's missing here, because from the spear phishing attachment, you get tool delivery. So you now have the capability to deliver a piece of malware, but you might not have that malware in the first place. So the next step is that I grant Lazarus group access to develop capabilities, which is 1587. And I run it again. So now they have access to malware, and then a whole lot more happens. At stage 3, we get user execution of a malicious file. Then they move on to internal discovery on the target system. They obtain persistence. They do privilege escalation. And they reach some of the other objectives like denial of service, destruction, computational resources, but they do not reach objective exfiltration. One of the missing pieces for reaching that is they don't have a command and control channel. So what they're missing to get a command and control channel is command and control infrastructure. They don't have any technique that gives them command and control infrastructure. There is a technique called acquire infrastructure, which I can give them, assuming that Lazarus group has access to command and control infrastructure. And that technique is 1583. We run it again. So the main difference here, this is not that much more exciting than the previous execution, but at this point, they're able to establish command and control, which gives them the promised adversary control communication channel. So, okay, they're still not able to complete their objective, which is exfiltration. The last missing piece here is that they're not able to do lateral movement because they do not know about other hosts and services in the infrastructure, which is a requirement for moving laterally. So I will give them the technique network service scanning, which is number 1046, and run it again. And at this point, the tool says success, because what happened now is that at stage 7, they move laterally using remote desktop protocol. At stage 8, they collect data from local system, which gives them the target information. And at stage 9, they archive, stage, and exfiltrate that data, which reaches objective exfiltration. So just a quick, this was a threat actor. We also have incidents here. So just a quick example of a SolarWinds incident, without giving them any pre-seeded techniques. I just run it with the attack navigator layer that describes the SolarWinds incident. They're actually able to do quite a lot because they start off with supply chain compromise. They obtain execution, defense evasion, persistence, command and control channel, privilege escalation, but they are missing some techniques to get all the way to exfiltration. So there are some missing parts here, but at least the first 4 stages of the attack or intrusion are pretty complete compared to Lazarus Group. So back to the presentation. That was a demo. Then I want to talk a little bit about some issues that we have. These are not necessarily issues with attack, that there is something wrong with it, but it's an issue for how we use attack. So the first issue we have is that the tactics, defense, evasion, and persistence, they don't really drive an attack chain any further. They might be necessary for an adversary to avoid detection and to be able to come back at a later time, but they don't let you progress to the next stage of the intrusion. So for those techniques, we basically just say that, okay, you achieved persistence, you achieved defense evasion, but those promises are not used by or required by any other techniques. The main issue we have with attack is that attack basically consists of 2 different types of techniques. The first one is we call how it's done techniques, like exploit public facing application. Those techniques describe what an adversary does, and they map pretty well to what we've been doing, because you can identify what the prerequisites or requirements are, and you can identify what you get when you do it. So those techniques are fine. The main issue is that attack also contains what we call what you get techniques, like valid accounts, that don't really describe adversary behavior. They describe what the adversary gets, which more or less maps to our provides promises. So we had issues with that. We've tried to get around it, but ideally, we would hope that all techniques should be how it's done techniques, describing how the adversary behaves rather than what they get. So an interesting side effect of what we did was that we pretty quickly started identifying missing techniques and sub-techniques. And from the demo, you could see that iteratively, you can identify candidates for missing techniques, which takes the generation of the attack stage 1 step further. We also have some functionality in the tool that I didn't show to help identify or pinpoint exactly which promises are missing and which techniques that might provide those promises. So we've already had 1 submission to MITRE of missing techniques, and we hope to have more in the future. So the tool also can help as a quality assurance tool. There's a bunch of caveats. The first one is that I used Lazarus Group as an example, but it actually is quite a bad example because adversary groups in MITRE ATT&CK are linked to techniques that have been observed over a very long period of time. So in some cases, you might have aggregated techniques that have been observed over a period of more than 10 years. And if we keep doing this in the future, we might have adversary groups with a long list of techniques that have been observed over the time span of decades. So those techniques don't really tell you what that adversary has been doing recently. So the best source of techniques to be used with this tool is actually from incidents or campaigns. So you have a clear time frame in which you have observed these techniques. That being said, there are not that many good sources of techniques except for MITRE ATT&CK. So I don't really see any good alternatives at the moment. But ideally, techniques should be linked to incidents and campaigns in addition to threat actors. Also keep in mind that what we've been doing here, we're not considering any specific infrastructure. We're not simulating attack or an attack on a specific infrastructure. What the tool tells you is these are all the options that the adversary has at each stage of the intrusion. But those are options. Those are not necessarily what they would choose to do, but if you just look at one path through these options, that might be an attack. So to visualize this as a graph, you would have edges going out to lots and lots of nodes further down, but one path through that graph would be an attack. So you don't get that one path from the tool, but you get all the possibilities. Then our vocabulary. Our vocabulary doesn't cover everything. It's not finished, and we're still working on it. And we're probably going to change it in the future. And finally, there's probably mapping bias at play as well. We're humans, we do mistakes. And when we assign promises to the requires and provides, that's a little bit subjective. It depends on the experience and the expertise of the analyst, which kind of brings me to future work, because we're not able to finish this on our own. What we want to achieve is to develop a standard vocabulary of promises for this that's accepted across the industry. And that's not something we can do on our own. So we're hoping that others will see the value of this and see that this might be a useful way to automate generation of attack stages. And then we can collaborate on bringing this further, and maybe even bring it into a standardization body at some point. So if you're interested in that, then please interact with us on GitHub or contact us. I will be happy to collaborate. The next step would be attack integration. So whenever you add the new technique to attack, in addition to what's done today, you also define the promises provided by and required by that technique. Because once you've done a job of mapping all the existing techniques, the extra effort of mapping new techniques is negligible compared to the big job of doing it to the techniques currently in attack. And it's very useful. We also want to integrate this in the Socrates platform. I'll get back to that in the next slide. And finally, more ambitious is that sometime in the future, we would hope to develop structured procedure definitions to address the actual emulation plan part of this, so that you can take even further steps to automatically generate a full adversary emulation plan. So finally, on the Socrates project, The Socrates project is an innovation project that builds security automation and decision support platform for SOCs and CSRTs. It has a webpage at socrates.eu, and the project is also looking for new members of the stakeholder group. So if you're interested and think this sounds interesting, please consider signing up for the stakeholder group. That's all from me, and thank you very much.